Hi. Okay, then we can begin, yeah?
Great.
Then welcome everybody to the JINA online seminar. Our speaker today is Andrew da Silva Schneider. He got his PhD with Chuck in Indiana and then afterwards became postdoc at Caltech, and he will tell us about the nuclear equation of state for astrophysical simulations. And please, during the talk, mute your microphones so that we can only hear the speaker.
I was about to mute mine. Okay, thank you everyone for joining us here. So I'm going to talk a little about this work I've been doing at Caltech with Luke Roberts from Michigan State and Christian Ott also from Caltech, which is about nuclear equation of state for astrophysical simulation. So we started this work because we wanted to do some simulations of accretion-induced collapse of white dwarfs into neutron stars, but we couldn't do it because the equations of state that we had available were not working. So instead, we decided to just work on developing our own equation of state so we could do that type of simulation. And we still haven't gotten that far, but we've developed a bunch of new equations of state that we can use for simulations. So here, for the purpose of this talk, I just consider that the equation of state is how the thermodynamical quantities of matter change as a function of the density and the proton fraction or electron fraction y and the temperature T. And this has a lot of relevance for the type of work we do because we want to simulate things like core collapse supernova. We want to know what the neutron star structure and how it evolves over time is. And also we want to study compact star mergers. I guess this is a hot topic right now since the event a few weeks ago. And this is not an easy problem because we have huge ranges of density, temperatures, and proton fractions that we have to explore in order to have a consistent equation of state. So here, for example, I have the simulation of a 15 solar mass, or a star that was 15 solar masses in its zero H-band sequence, and how it evolved over time over its 500 milliseconds after it started its collapse, or sorry, after bounce. And you can see that the density across the star changed by almost 10 orders of magnitude as the star collapsed to form a neutron star. The temperature changed by a couple of orders of magnitude from a tenth of an MeV to 50, 60 MeV. And you can see that the proton fractions across the star, it started at almost symmetric nuclear matter when the star didn't have that much of a high density. And then as it collapsed, the proton fraction of the matter decreased a lot and became very neutron rich. If we do a similar plot for a 40 solar mass star, then we see about the same thing, same order of magnitude of changes in density. The temperature now it's even a bit higher, that's almost 200 MeV, and similar ranges in proton fraction. And here is a similar plot for a neutron star merger. And you can see the temperatures don't get as high. You have a linear scale now in temperature, but the proton fractions get much lower, almost close to pure neutron matter. So we want to understand what the properties, the thermodynamical properties of matter are in this huge range of density, temperatures, and proton fractions. So we have to collect information about this parts of the parameter space from several different experiments and observations, so we can get some information from heavy ion collisions. We can use nuclear reactions and nuclei properties to constrain the thermodynamical properties of matter in other regions of parameter space. We can observe astrophysical phenomena and then try to infer some properties about what happens at high densities, depending on what you observe from the gravitational waves strain as two neutron stars merge. Other observations, you can observe some neutron stars accrete material from a nearby star, and then they heat up and they cool down over time. And from the cooling curve, you can try to infer the properties of the radius and the mass of that star, and that will also give you some constraints on what the matter looks like at high densities. You can do some simulations of dense matter. Here I showed some nuclear pasta simulations that I and others did with Chuck some years ago. So at high densities, right below nuclear saturation density, you can get matter to form not just spherical nuclei, as you see here, or not uniform matter. As matter goes from spherical nuclei to uniform, it can go through all these phase transitions, and this might have important consequences on how neutrinos interact with the matter in a collapsing star or during a neutron star mergers or in a cooling neutron star. And also you can do many body calculations, so you can just compute all this, these diagrams of the forces, 2 nucleon forces, 3 nucleon forces, and so on, and then you go further and further and see if your calculations are converging and try to obtain the properties from this, of matter from these calculations. One thing is that even though with all these different methods to obtain the properties of the neutron stars of matter, there are still regions where we have a lot of uncertainty. So basically, if you go above 2-3 times nuclear saturation density, you can't tell much about how matter is behaving. You can't obtain that directly in labs here on Earth, and then you don't have that many observations from, say, gravitational waves from neutron star mergers or none from supernova to try to infer what happens at these high densities. Also in the region just below nuclear saturation density, where you have all the pasta phases, we rely mostly on numerical simulations to obtain all the properties of matter there are. And we can produce nuclear pasta on labs, so we have to rely on model-dependent observations of neutron star cooling or on numerical simulations. And also we can produce yet very neutron-rich matter, so if you go below, say, 30–25% proton fraction, then there's a lot of uncertainty of what happens to matter over there. So even with all these challenges, we want to compute a hot-density equation of state so that we can use on our simulations of core collapse supernova, neutron star mergers, and so that we want to simulate these events. And even with all those uncertainties, we still have to have what the equation of state looks like within the constraints that we have obtained so that we can simulate them. So the basic is just you add the particles you want in the equation of state. So here, say we add protons, neutrons, electrons, photons. That's I guess the bare minimum you can add to have a decent nuclear equation of state to use in the simulations. Then you decide whether you want to use realistic potentials between the nuclear interactions or you just use some simplified effective potentials. You can make your model use relativistic equations of non-relativistic. You can then, once you have the particles and the models and the interactions, maybe you want to make a simplified problem that we call the SNA, where nucleons cluster to form nuclei. And do you want all those nucleons to cluster to form just one type of nuclei? So that would be the single nucleus approximation. Or could it form multiple types of nuclei, which would be the nuclear statistical equilibrium if you consider just the ground state. So you can have an ensemble of nuclei or just one nuclei, or you can even use reaction networks. You can do that to simulate the evolution of star from zero age up to collapse. But once collapse starts, this happens so fast that if you try to keep track of all the reactions going on, you're gonna need too much computational power to actually do that. So usually you just consider that once the collapse starts, matter goes into equilibrium, and then if you have multiple nuclei, use nuclear statistical equilibrium, or you can consider just one type of nuclei and use the single nucleus approximation. And then you can do something a bit more complicated, or not too much, if you add positrons and muons, but you might want to add other particles such as pions, hyperons, and even quarks if you go to too high density. So there's a few EOSs available, and here are the main ones that are used, and mine at the bottom. And so most of these EOSs, you can find the tabulations, the tables online that you can just use in our simulations. And then if you need a value that's not on the table, you just interpolate between the values that are there. So there's all these EOSs, but then one of the issues with them, or that we found, is that if there is, say, a nuclear physics constraint that is being measured with higher accuracy after these EOSs have been developed, you can't, they don't obey some constraint that you now know is correct, for example, that might change the results of your simulation. So you can't go back and redo all these EOSs to fit this new constraint. So one of the things that we wanted to do was to have a code that if a new constraint is measured, then you can go in the code, put this new constraint, and then the code gives you an equation of state that satisfies this new constraint. So we developed this code called the SRO-EOS code, and it's a modular Fortran 90 code. It computes the equation of state based on the liquid drop model. So the model is very similar to the Latimer-Swasey model that's been here since the 90s. So it uses skirm interactions for the nucleons, and the code is open source. So you can just go to this site and website, download it, and then you put in your favorite parameterization for the skirm forces between nuclei, and then you can generate an equation of state for your simulation. So you don't depend on the ones that are already available that might not satisfy some constraint that you want to study, or you want to do some sensitivity studies and just change one of the constraints in the nuclear force and see how it affects your simulations. So you can download the code and basically put the parameterization there, and then it will give you an equation of state. And then there's some results on the archive for a while, and it's just been accepted for publication in PRC, so it should be out soon. So what's the Latimer-Swasey equation of state? So this is one of the most used equations of state for core collapse supernova simulations and for some neutron star mergers. It's based on a non-relativistic compressed liquid drop model description of nuclei. So in this model, we only care about nucleons, so we only add protons and neutrons. We add alpha particles just as hard spheres, so they add an exclusion volume to the system. Then you add electrons, positrons, and photons. So the electrons and photons just form a background gas. And the nucleons, the protons and neutrons, they may cluster to form nuclei, and then they just form one type of nuclei. So it's a representative nuclei of all the different type of nuclei that can show up in the system at a given density, temperature, and proton fraction. And this nuclei is surrounded by a low density nucleon gas. So you also have some nuclei outside of the heavy nucleus. And then you compute the chemical and pressure equilibrium inside and outside nuclei. So here's a picture from a paper from Latimer and Prakash from a year or so ago. So here's basically if you fix the proton fraction and then you do this plot of temperature as a function of density, you can have basically three distinct phases of matter. So phase one, you have a low density uniform phase. So you can see it here. You just have a background sea of electrons, and then you have some neutrons and protons and some alpha particles immersed in this background sea of electrons and photons. Then in phase two is where the heavy nuclei form. And then you'll have a low density gas of protons and neutrons and alpha particles, and then you have this nuclei surrounded by this low density gas. And then if you go to very high densities, then you get the phase three where nuclei dissociate, and you basically have, again, uniform sea of nuclei and electrons, but then it's so dense that you don't get many alpha particles there. So this is what the energy density looks like in this skirm type of interactions. So the energy density is a function of the density, proton fraction, and temperature, and it depends on this parameter. So you have a kinetic term here, these first two terms that depend on the effective mass of neutrons and protons, and the stall terms, which depend on the temperature. So all the temperature dependence of the system comes into the stall terms, and then you have the potential energy terms that depend on the density of the system and the proton fraction. And then you have these red parameters A, B, C, D, and delta, who specify what the force between the nucleons are. And then the effective mass also depend on two other parameters, alpha 1 and alpha 2, that we can obtain different values for different parameterizations. And if you're familiar with skirm type interaction, these A, B, C, D deltas and alpha parameters are related to the X and T parameters and sigma that usually have on skirm parameterizations. So you can find hundreds of these in the literature, and then you can just fit in, you obtain these other parameters, A, B, C, D, and then you plug into this equation for the interactions and you obtain the equation of state. So okay. So instead of talking about the energy density, I'll talk a bit about the free energy of the system, which has several components. So you have the free energy of the nucleons that are in the gas outside of nuclei. You have the energy of the heavy nuclei. You have the free energy of alpha particles, electrons, and photons. The leptons and photons, you can solve them separately, given a density and a proton fraction and temperature. You just assume that they are background gas, so they don't complicate solving the system too much. The main problem is try to find the equilibrium at a given density, proton fraction, and temperature of what the size of the nuclei are, what the density of alpha particles and nucleons outside of nuclei is. And the heavy nuclei free energy depends on what the nucleons inside the nuclei are doing, and then you have some surface terms, Coulomb terms, and the translational energy terms. So I'm not going to spend too much time on this, but just the surface and Coulomb terms. Yeah, okay. So the total free energy is going to depend on 7 variables. So the volume fraction that's occupied by the heavy nuclei, the size of the heavy nuclei, the densities inside and outside of nuclei, and the density of alpha particle. And then we will minimize the free energy with respect to the 7 variables and figure out what the ground state of the system is. And so we have 7 equations we need to solve, but we can simplify this and just solve 3 equations and have 4 constraints, such as conservation of charge, conservation of mass, conservation of charge. There is one equation that relates the density of alpha particles to the density of neutrons outside heavy nuclei and inside. And the generalized size of the heavy nuclei you can obtain from the nuclear virial term. So basically, we're just solving the 3 equations for the volume fraction of nuclei occupied and the neutron densities and proton densities, inside heavy nuclei. And this simplifies a lot how we solve the system. We need to deal with the pasta phases. We use an approximation to do it, so that we try to find what type of shape of nuclei would minimize the energy, the total energy of the system. And then if you choose a spherical shape for the nuclei, it's going to have some energy, and then if you choose a cylindrical, it's going to have a bit of a higher energy at some point, but then it becomes dominant at some higher density where the occupied fraction by heavy nuclei is higher, and so on. But then instead of trying to solve for all these different possible shapes, we just approximate this curve by some function that just depends on the average volume occupied by heavy nuclei. So this also simplifies our problem quite a bit, instead of trying to look for which of these phases or even other phases would minimize the energy. So here is just a plot of the pressure of, we got the Latimer-Swesty parameterization and plugged into our code. And then we compare with the actual Latimer-Swesty pressure obtained with the code from Latimer and Swesty that's also available online. So this is just comparing the nuclear pressure. And then I have here some thick black lines that tell you where the different phases 1, 2, and 3 that I showed a couple of plots ago were. So where heavy nuclei form and where they don't. And the 2 codes agree pretty well. So that was encouraging. You see a few differences at very low temperatures where the Latimer-Swesty code fails to converge and find a non-uniform solution. So it just assumes that the solution there is uniform. In our code, you're able to get nuclei here. So that shows some difference in the pressure. There are some other parts where you get also some differences from the codes not converging, or from the Latimer-Swesty code actually having a lower tolerance to, accepting higher tolerance to error in some quantities than ours. So a few years ago, Dutra and collaborators, they analyzed over 240 Skirm parameterizations that are available in the literature. And they found that only 11 of those parameterizations fulfilled all the current established nuclear physics constraints. And then if you get all those 11 and you try to look at neutron star mass radius relationships, only a few of them actually get close to 2 solar masses. So we got these 11 parameterizations. We produced the equations of state tables for them. They are also available online if you don't want to use the code and just download the tables. And then we computed the mass radius relationships for neutron stars. And you can see here that most of them fail to get to 2 solar masses. Only 3 or 4 of them get above 1.9, and then we also have this. The SKT1 parameterization produces kind of low neutron star maximum mass of about 1.8, but then we add some terms to make the equation of state stiffer at high densities, and then they're able to produce the heavy solar mass. So that's another thing. We can add terms to the equation, to the Skirm parameterization that don't affect the equation of state where you know it's all constrained, say below 3 times saturation density. But you can make it stiffer at high density, so you produce high mass neutron stars. one of the things that is that we can do also, you can get some, say, chiral effective theory parameter, and you can get some curves for the energy as a function of density, and then you can use a SKRM parameterization to fit these curves. So now you have a new parameterization that you can use to obtain an equation of state. So it's kind of simple to do. Jeremy Lim and Yan Huan Lin and Jeremy Ho did this earlier this year. Then I got this parameterization plugged into my code, and it kind of worked well. So that's another powerful thing that you can do now. Even if you don't obtain the SKRM parameters by looking at you can just obtain the equation of state in a different way, and then you can just fit SKRM parameters to it and then produce an equation of state. Okay, so one way I've been doing this lately is that, so we often expand the nuclear energy density as having a kinetic term and a potential term. And then the potential term you can expand as having an isoscalar term and an isovector term. And the isovector term depends on the asymmetry of the system, and the isoscalar term depends on, it basically tells you how symmetric nuclear matter behave. And here you have the usual terms that express the equation of state with the energy at saturation density, the symmetry energy, the slope of the symmetry energy, the incompressibility, and then you have higher order terms. And then you can, for a set of these terms that you can usually, some of them obtain experimentally, others theoretically, you can just compute the SKRM parameterization and do this SKRM parameterization to obtain a new equation of state. But all of these terms are obtained near saturation density, so they don't constrain the US too much in the region, say 4 or 5 times nuclear saturation density, which are important for neutron stars. So another way you could do it is just, instead of, you could compute from the SKRM model what the pressure looks like at high densities, and then try to fit the pressure, say, at 4 or 5 times nuclear saturation density with some experimental constraints. So these are some constraints that were computed by Danielowitz and collaborators some years ago. So one of the thing that I've been doing is just get the experimental constraints for some of these quantities. Some of them are more like theoretical constraints because they haven't been measured. And then use this pressure at, say, 4 times nuclear saturation density to obtain the other terms in your expansion. So the terms higher than third order or so, they would be given instead of having to see their constraints and obtain the SKRM parameters, you can obtain the SKRM parameters and the values of these parameters by looking what the pressure is at a much higher density. And then, so this was done in a certain way by Margaron and collaborators earlier this year, and they study how cold neutron stars are affected by the different parameters. And so what I did recently was just vary those parameters and get a bunch of new equations of state. So there, I guess, we produced about 4,000 equations of state, and about 2,000 of them fulfill the 2 solar masses constraint. And then you can just get one that has a neutron mass radius relationship that you like, and then make a hot equation of state, and then try to make a simulation with that and see what the effects are. Some of the drawbacks of this approach of using the SKRM parameterization is that the equation of state can become acasual at high density, so the speed of sound becomes higher than the speed of light. But then there's a possible fix that I, here at Ohio, try to work with Konstantin and Prakash and add this to our code so that you don't have this issue. Okay. How much time do I have? Another 10 minutes. Okay, so all of this is done in the single nucleus approximation. One of the things we added to the code too is add a nuclear statistical equilibrium at low densities. So it's kind of easier to solve. You just give an ensemble of nuclei, sometimes thousands of nuclei, and then you just solve for the 2 chemical potentials that put all the nuclei in equilibrium at a certain density, temperature, and proton fraction. So this is a bit easier to solve, and then we can obtain the equation of state at low density using thousands of nuclei. One of the reasons we do this is because the single nucleus approximation, the properties of certain nuclei differ considerably from the actual properties of from the properties you actually measure. And also in the single nucleus approximation, you don't consider things like shell closure. There is no pairing, at least in our approach, and you neglect lots of many body effects. On the other hand, the nuclear statistical equilibrium breaks down when you get close to saturation density, where, say, the nuclear pasta phase forms, and you don't have any information about the size of the nuclei that are formed. And then also at very neutron-rich nuclei, where you don't have much information about the binding energy of nuclei there, or the masses, you can't really can't rely on the nuclear statistical equilibrium approximation too much. So use this ad hoc procedure just to mix from the single nucleus approximation to the nuclear statistical equilibrium computations. And you just fit it by considering this function chi that's just a function of density, and it should, if chi goes to 1, then you are in the regime of, you only consider the single nucleus approximation, so near saturation density, say, and then if chi goes to 0, you just are in the regime or you only consider nuclear statistical equilibrium. So you're way below saturation density, then you might want to rely more on this approximation. And then you can obtain some correction to the thermodynamical quantities. So if you compute the pressure, for example, because this function depends on the density, it's not just going to be a direct sum like the free energy was, but you also get these correction terms that depend on the difference in free energy. But the equation of state is self-consistent if we do this computation. So here's more or less what it looks like. So at low densities, you have nuclear statistical equilibrium, then you have a transition region, then you have the single nucleus approximation region, or where matter also gets uniform, and then at high densities, you can also add some modifications to the US if you want to make it stiffer or softer. And I'm going to talk a little bit about the core collapse supernova simulations that we've been doing. So what you do is, to get the initial conditions for your core collapse supernova simulation, you use a stellar evolution code. So you have Kepler, Mesa, there are probably others. You start with the initial mass, initial composition for the star, and you just use reaction networks to evolve this over time until the star starts to collapse. The star loses lots of mass due to stellar winds. This depends a lot on the metallicity of the star, so you have to consider that too in your simulations of the stellar evolution. Okay, and then the star starts to collapse at some point. So you get this, whatever the star looks like from your stellar evolution code, and then you put in your core collapse code. And at that point, the star is still not in nuclear statistical equilibrium, or so that's one of the issues, is that not all the thermodynamical quantities that you obtain for the stellar evolution, say the density, temperature, electron fraction as a function of the radii, entropy, pressure, composition, and so on, because they can, not all of them can be matched to our equation of state. You can pick at most 3 of these quantities and that were obtained from your stellar evolution code, and then match to your equation of state table, and then put it on your core collapse supernova code. So say, we usually fix the density, the proton fraction, and the pressure, and then you obtain the other quantities from the equation of state table. So if I show here a plot of a composition obtained by the, I think it was obtained by the Kepler code for a 15 solar mass star, you have this temperature at the core of the star at the start of collapse. But then we can't match all the thermodynamical quantities. So because we chose the density, proton fraction, and pressure, the temperature and entropy are going to be different once we move to the stellar collapse code. And this is an issue, a little bit of an issue, because it might depend on how you match. Which quantities you match might make a huge difference on what your collapse looks like, and also which equation of state you use. So if you use say a nuclear statistical equilibrium, 23 nuclei, you get a bit of a higher temperature, and then if you use 3000, it's a bit higher. If you use the Latimer-Sweste equation of state, you get a much higher temperature, and then I guess the SLI4, in the regions where there are some discontinuities in the density and thus the other quantities such as the temperature and entropy, this parameterization gives huge, well, much larger kinks than actually are observed in your stellar evolution code. So this might make a huge difference when you simulate your supernova, the fact that you can't match all of the thermodynamical quantities at this point. still we do our simulations, and then we obtain here, for example, the density at the center of the star, depending on each of the equations of state we use. And then they form one band, and there's some differences between them, but there doesn't seem to be a pattern here, or except, yeah. But then when you go to the temperature at the center of the star, then you have a large difference between a few equations of state. And it depends a lot on how they treat their effective masses. So in the Latimer-Swesty equation of state, that is the most used one, it produces much lower central temperatures than all the other equations of state that we tried, except for the other equations of state that also consider that the effective mass of, the effective masses are equal to the vacuum masses. So this produces lower temperatures at the core than the other equations of state that produces, that say that the effective mass is around 0.7, 0.8 times the mass of neutrons in vacuum. We also did a study on how the shock radius and the size of nuclei change if on the low density region I just used a single nucleus approximation. So this is done with the Latimer-Swesty 220 equation of state, or if we use an ensemble of nuclei at low densities. So if you use an ensemble of nuclei, you usually get a little bit, 10% or so smaller shock radii for the collapsing star. But the largest difference is in the size of nuclei, which might make a difference of how neutrinos interact with the collapsing material. We simulated a 4D solar mass collapse. So how long it took from the star to bounce and then to form a black hole. Depends a lot on the different equations of state, and it might vary up to, I don't know, half of a second. So yeah, so it just changes how long it takes to make a black hole depending on the properties of your equation of state. So now that we just did this for the Skirm parameterizations that are available in literature, now we can say keep all of the equation of state properties constant and then change one, say the incompressibility to its values, and see how the incompressibility would change the time to form a black hole, and then keep the incompressibility constant and change something else. So we could do some sensitivity studies now that we have this formalism. So I'll summarize. So we generalized the Latimer-Swesty formalism to obtain dense equations of state for most current parameterizations. Our code converges for a larger region of parameter space, and we generated many new equations of state, and we're able to generate as many as one now to study, and then you can use them to study core collapse supernova, neutron star mergers, and so on. Some stuff we're doing right now, we're studying the equation of state effects on core collapse supernova. We're doing 1D, 2D, and 3D simulations. 2D and 3D are very expensive, so you can't do much of them. So try to see what the effects are on 1D, and then try to see what would be relevant to study in the higher dimensions. We could improve the code a lot. We could add neutron skins to the heavy nuclei. This is going to have a large effect at very high proton fractions. We can add muons and pions at high densities and temperatures. This might have some effect on the collapse and on core collapse supernova. We can also, within the Skirm framework, instead of using a single nucleus approximation, add a nuclear ensemble. So this is one of the things I guess I'm doing here with Prakash and Konstantina, Ohio University. Can also fix the speed of sound at very high density, so it doesn't get larger than the speed of light. And then I guess one thing we could try to do, maybe not in the so near future because it could take a while, is make a relativistic version of the code. There are some relativistic equations of state out there, but they fulfill certain constraints, and I'm not aware of any of these codes being available, so you can use them to obtain new equations of state. And that's about it. Thank you.
Thank you very much for this very nice talk. If there are any questions? Okay. If there are any questions, then please indicate in the chat. And I think that while we're waiting, maybe the people in Ohio can go ahead if they have questions.
Not sure they will. Nope. So you guys know.
Anyone else?
Can I ask you a question, Andre? So you have a bunch of different equations of state. I might have missed it, but how many of these actually fit all of the constraints that are available? And is there any correlation in the, you show a huge range in like central densities. How does this, is there a correlation for the ones that fit the constraints, or are they all over the board for those as well?
So the constraints I tried to use were these mostly. So these are mostly, most of them, some mixture of experimental and some theoretical constraints of what this quantity should look like. So all of these equations of state that I show on this plot, they satisfy all of those constraints. And
but not the neutron star radius constraints.
Yeah, no, yeah, some of them are a bit out of this. I could eliminate those two. So out of about 4,000 that I did, about 2,000 fulfilled the two solar mass constraints, but I didn't care about the radii constraints. So I could put that too and see how many fit and which regions I would be able to exclude from the parameter space if I consider that this current parameterization is okay and that these numbers are valid. I noticed that the pressure of symmetric nuclear matter and proton-neutron matter had to be on the high end of this range in order to be able to fulfill the two solar mass constraint. But that was about it. So does that answer your question?
I was thinking more about the plots closer to the end of your talk where you show like maybe 15 or so different equations of state.
Oh.
And yeah, so here you show that like there's a big difference in the results of supernova simulations.
Yes.
Depending on the equation of state, which,
here.
Yeah, like those, I don't know any of these except for LS220 and SFHO.
Yeah, so the first four, LS220, KD, SLY4, and then RAPR, are the ones that get to two solar masses and get the radius kind of correct. All the other ones, so from SQMC below, they don't satisfy the two solar mass constraint. Oh, there's SFHO here too, which I added for a different reason. I didn't talk about it. That's not the current parameterization.
Okay, and even those are not clumped together.
No.
So even between those, okay.
Yeah, I think the ones at the bottom is just the LS220 SFHO that satisfy the two solar mass constraint, and then the other three that kind of satisfy are here on the top. But so they don't make a distinction between the central temperature from the equations of state that get to two solar mass.
Okay, thanks.
Yeah.
Okay. MSU is next.
Okay, you got it unmuted. Yeah, so I think you had a discussion earlier about using NSE versus single nucleus, and you were talking about some density. That's you just passed a couple times. That one right there. Yeah. So right now you do single nucleus at densities of less than 10⁻³ saturation density. Why did you choose that upper limit for NSE?
I don't know. I didn't do an in-depth study of how changing where this region is, or the width of the region is. Is that something we're looking into? But I just thought that I guess if nuclei occupy less than, say, 1/100 of the volume, then maybe that would be a region where I could consider nuclei as like point particle, and they would be far apart enough that they wouldn't all be the same size. You could have different types of nuclei. It's just a hand wave argument of where to put this. I could move it. I want to move it around and see how it affects, say, the core collapse supernova simulations. Or it doesn't affect too much the mass radius relationship of neutron star because it's so low. And I don't think having an SE at too much high density would make too much.
Well, I mean, I was just looking at some calculations that, you know, if you're doing pasta at about 1% of saturation density, you're still having isolated drops.
Yes.
And then at higher, then it starts to go into the pasta shape. So, I mean, once it starts going in pasta shape, then I can see that going to SNA, because you have this very nice parameterization for different pasta shapes in the Latimer-Svesky that you could consider that's the only way to go. But it just seemed to me like maybe 10 to the minus 3 was a little bit on the low side. But you know.
Yeah.
Does that depend on temperature also?
No, the parameterization we put was just depending on the density profile. So, yeah, you're right. I could put at higher density because even here at 10 to the minus 2, say, it's still nuclei are far apart enough that they would be point particles and we could use NSE. So that's one of the studies we're still doing, how changing this region, the width and the position would change our results and if they would change too much.
Right.
But we haven't done that yet.
If no one else has a question, I had this question. Okay.
I have a really stupid question probably, but I don't know so much about this. So why did you choose to go back to Latimer-Svesky if there are all these newer equation of states? Usually people try to improve things, so aren't the newer ones better, or what's the picture there?
I'm sorry, what? Why use the Latimer-Svesky if there are other ones?
Yeah, and aren't the other ones better because they're newer?
Yeah, but there are more complicated models. So in this one, we could just, feels like it would be simpler to generate many more equations of state and not as computationally intensive. Also,
but this is an improvement of the Latimer-Svesky equation of state, right? Because you're
yeah.
using the effective masses, so you are
Yeah.
finite temperature calculation.
Yeah, so even though we based our model on the Latimer-Svesky, we did a few improvements over it. Say the Latimer-Svesky code, even though their formalism on the paper considers that the effective masses can change as a function of density and temperature. In this case, in their code implementation, it didn't. And also, we did a deeper treatment of the nuclear surfaces and Coulomb forms that is actually done in the code. So even though we based our formalism on theirs, but we just didn't copy it and redo everything. We added a few more things in order to improve it. But yeah, I guess all these other equations of state that are newer, yeah, they have somewhat different treatment of the nuclear forces. Most of them, I guess, are relativistic. But I don't know, we chose to go with the Latimer-Svesky from the start and just did what was possible. Maybe that's one of the things that I talk about in the last slide, is making a relativistic version of this code. And maybe that's something for the future. And then we could, within that code, if we do something similar to what we've done here, we would include all the other equations of state that have been done in the past. Most of them.
Can I ask a question? This is Sanjay. I'm sorry, I joined the talk a little bit late. The Latimer-Svesky has been criticized in the past for not reproducing low density properties of neutron matter. How does that affect your conclusions?
Yeah, so I guess if you look at these parameters, right, there are some of them that the Latimer-Svesky doesn't reproduce too well, or some of these combinations of parameters. So I guess we could kind of stop using the Latimer-Svesky equation of state because it doesn't fulfill some of these constraints. But with the code that we have now, you could just put these constraints in and obtain a square parameterization, so it would reproduce better what happens at low proton fractions. So even though the formalism is good, it
Okay, there are more questions at MSU.
Yeah, well, I have one question about a figure that was shown earlier, but I don't know what slide number that is, so you have to page back.
You mean the Latimer-Svesti to comparison?
Well, there was this figure, I didn't really understand what the colors meant. What's that?
Yeah, I think the ratio of viewers to Latimer-Svesti.
Yeah, sorry, Mike. F5. Right? Yeah, sorry, my computer turned off. Okay. Yeah, so,
Okay, I have a simple question. So, how does your equation of state? Can you use your equation of state to compare compute the tidal polarizability and compare to the neutron star merger results?
I'm sorry, could you repeat part of the question?
The new neutron star merger result that have the polarizability, tidal polarizability. So how you can use your equation of state to compute that supposedly, right?
Yeah, I think so, but I haven't.
So
never.
Yeah.
Done that. So
okay.
I guess I could get a few of these thousands of equations of state and see which ones.
Not 2,000.
Well, I think the more interesting question is what in detail does the equation? So you have many different densities and different different phases in the matter, and the question is there what is the most important aspect of the equation of state to describe the tidal polarizabilities? That would be really interesting to know. Because I mean, the results that are shown basically are a couple of stock equations of state. Some of them we know are wrong. That's in the paper, and it would be nice to know what the actual sensitivities are.
Or for example, what density region is it sensitive to?
The density, yeah. What density region is sensitive to, and of course that would require some communication with people that can do the dynamics, but.
Yeah.
The tidal polarizability is largely determined by the radius of the neutron star, and it is weakly dependent on the internal distribution of matter. So this has been studied quite extensively. So the same physics that determines the radius of a neutron star also determines its tidal polarizability. So between two and 3 times nuclear density is probably what dominates.
But another question though is when you take a look at the matter that comes out, for example, to do our process, is that also then dictated by that density region, or is it also important to know what it is in lower densities or even higher densities? It seems lower densities are more likely, but
yeah,
because
when you want to study the ejecting detail, maybe all of the properties are okay, but then you get out of equilibrium, right? Quickly as the material expands, so you'd have to use a different approach, because here we only consider material that's in equilibrium.
Well, I mean, isn't it fairly close to local equilibrium? I mean, it's not equilibrium everywhere, but I mean, the time scales are still relatively long, isn't it?
Yeah. So someone said here that not the interesting part.
I didn't hear that comment.
Yeah. So
I was just saying not the interesting part, right? So when it's in equilibrium, I mean, that's just the nuclear mass is determined to abundance. So you care about the equilibrium.
I'm sorry, can you repeat that again with a little bit better control of your proximity to the microphone?
Zach, I was just saying that don't you care about the part where it's out of equilibrium? I mean, that's where, that's where the interesting stuff happens.
Well, there are two kinds of equilibrium. There's mechanical equilibrium, which is certainly not satisfied, and then there's also local thermal equilibrium, which I would suspect is satisfied. But I don't know.
Yeah, we could probably determine the initial conditions, how they depend on the equation of state for the ejected material, but not what happens to it after it's been ejected.
Okay.
Sorry, there's another question from NCSU.
Yeah, I was just, so you showed that there's a big mismatch between the stellar models that are input to core collapse simulations and the thermodynamic variables that end up being used from the equation of state. Is that a large error? And I mean, for the results of the core collapse simulation, do you get significantly different answers if you choose the pressure as opposed to the temperature? And might it be reasonable in the future to use the same equation of state to evolve both the progenitor and the collapse?
Yeah, I guess that would be ideal, but I guess that's one of the things that we talk about, is that we could probably evolve the equation of state, whatever nuclear reaction network you have further, even during the collapse, until it reached nuclear statistical equilibrium. But,
right, but so you have NSE imposed in the low density parts of your equation of state, right?
Right. Yes.
Is that something that would be reasonably extendable to take input as input the whatever abundance fractions dynamically during a simulation, or is that something that's really has to be fixed beforehand?
Yeah, I'm not sure how we would do that, because the tables are not too large, like they are 1 gigabyte, but then, or half of that. But then if you add another variable, say what the composition is at the low densities, you could still compute what the free energies and all the thermodynamics are, but I think it would just get too large. So it might not be feasible. But there might be other ways to approach the problem.
And just the first thing that I asked that I sort of walked over myself about is the choice of thermodynamic variables. How important is that for the result of the simulation?
Oh yeah, so initially when we were doing the simulations, instead of picking density, proton fraction, and pressure, we were picking density, proton fraction, and temperature. And that changed our results a lot, because I think the pressure is more important in this case for the dynamics of the system than the temperature. And if you pick the pressure, if you pick the temperature instead of the pressure, there are even some of these stars, say the 15 solar masses, they wouldn't even collapse. They would just kind of bounce back right away and not form a neutron star. All the material was being ejected, which was kind of unreasonable. And that happened mostly for, I guess the SLY4 was one of them, because the pressure difference at the center, once we matched the temperature, was too high. We got too high of a pressure, then the star wasn't collapsing. So it does make a large difference which quantities you pick. I'm not sure what the right way to be. Ideally, we would match all of the thermodynamic quantities, but that's just not possible.
Right. Okay. Thanks.
So that's something to prove.
Any other questions? If not, let's thank Andre again. Bye-bye. Thanks, Andre.